as well. Okay, and we are going to start in 3, 2, and 1. Okay, we are going to get close to finishing 5.2 today. We're not going to quite get there. But as you know, we are looking at bond vibrations. Now, I know it's really exciting, but I do need you to be quiet so everyone else can hear. Thank you. As a note, please make sure you bring your model kit starting Monday. We're going to be using your model kit for basically the rest of the term. So make sure you bring it. Okay, so we're talking about bond vibrations. Every bond in a functional group has its own unique characteristic vibrational frequency. If light of that frequency hits that bond absorbs that IR energy, it gets excited, and we can detect that absorption with an IR spectrometer. Depending on what type of light it absorbs, what the energy of that light is, what its frequency is, or 1 over wavelength is wave number. It's just another way about talking about the energy of the light. We can see what type of light it absorbs, and different bonds absorb different energies of light. So last class, we finished off by looking at a spectra, an IR spectra, and we saw we can see when the sample absorbs different wavelengths or different wave numbers of light. So now we're going to look at this handy table that you have in your workbook. And the first thing I want to draw your attention to is that this table is provided on tests and exams. So number 1, don't memorize it. Save your brain cells for something else, but we do want to learn how to use it. So in your workbook, we're going to work through here, and you can start making some notes as we work through this table. So we're going to start up here. Remember how I said in topic 5.1, we're identifying these functional groups, but then we want to do something more useful with it. And here's an example of how we're going to do that. So when we see alkyl, we know we're talking about an alkane or the alkyl portion, carbon-carbon single bonds in an organic molecule. Well, if a molecule has a carbon-hydrogen single bond and the carbon has all single bonds, that means that's an sp3 hybridized carbon. And this matters, that's why we're emphasizing it. If a molecule contains a carbon-hydrogen bond where the carbon is sp3 hybridized, that means that normal vibrational frequency, its ground state vibration, will absorb IR light in the 2800 to 2900 wave number region. So we would expect to see some type of absorption peak at that wave number. The relative intensity of that is going to be medium strong. So of course it depends on the concentration of the sample, but if it's medium strong, that means it's going quite a ways into that spectra. The transmittance is going to be very low because the sample is absorbing that energy at that particular wavelength. If we see a peak at around 2900 wave numbers, odds are it's an sp3 carbon-hydrogen bond vibration. Well, now let's go to an alkenyl group. If we have a carbon with a double bond, then that means it's going to be sp2 hybridized, or at least if it's a carbon with a hydrogen there. sp2 carbon-hydrogen bond vibration happens around 3000 wave numbers. So you can see the wave number has increased, and energy, as we saw on our first slide and last class, is directly proportional to that wave number. So energy is proportional to frequency, energy is proportional to wave number. As the wave number increases, that means that bond energy and bond frequency and bond wave number is also increasing. So going from an sp3 to an sp2 hybridized carbon, the frequency and the wave number of that bond has increased. And we're expecting some type of medium-ish peak. Well, now let's move to an alkynyl bond, or an alkynyl functional group. That means a carbon with a triple bond. So now we're looking at an sp hybridized carbon with a single bond to hydrogen. That particular bond tends to absorb light in the 3300 wave number region. So again, slightly higher energy. And this one's a little more unique. This one is called a strong intensity. So we're going to see that as a very diagnostic peak. It's going to be really bold and stand out and more obvious to us as we're looking at it. And then we go to our aromatic groups, and we know that this is when we have the double single carbon bond. So the carbon-carbon bond has a bond order of about, ooh, that's interesting, of about 1.5. Who knows how to turn that off? Okay, we're going to pause and we'll continue. Okay, carbon-carbon bond in an aromatic group has a bond order of about 1.5. We just won't draw in that region. Okay, but we're still talking about an sp2 hybridized carbon that has a single bond to hydrogen. This sp2 carbon-hydrogen bond vibrates and absorbs light at around 3030 wave numbers. You can see that's very similar to the alkenyl sp2 carbon-hydrogen bond because they're both sp2 carbon to hydrogen bond. So they're very similar. Based on that, it would be kind of hard to distinguish them. 3030 falls within 3010 to 3095. But we see some patterns here. So there must be some rationale, some reason to this pattern that we're observing. So we've seen as the hybridization of that carbon changes, the type of light that it absorbs changes as well. Okay, now let's look at bond order. In an alkyl functional group, we're back to the top, so an alkane, carbon-carbon single bonds, we're looking at a bond order of 1. Now, I'd like you to add this to your table. This value isn't included in your table because it's not in the diagnostic region. This wave number falls in the fingerprint region where it's a little harder to identify these peaks, but I think it's helpful for the comparisons that we're going to make. So if we have a carbon-carbon single bond, it tends to absorb light around 1200 wave numbers. Well, now let's go up to our aromatic group. So we're down at the bottom of the table now. It says a carbon-carbon double bond in your table, but we know it's really a bond order of 1.5 because aromatic is when we have that double single pattern. And we can see it absorbs light in the 14 to 1600 wave number region. These numbers often have ranges because the energy that it absorbs can be slightly higher and slightly lower depending on the other atoms and other functional groups in that region. So that's why we have a range. So bond order of 1.5, we've increased the energy that it's absorbed by that bond vibration. So it has a more energetic frequency, around 14 to 1600. And then we'll go up to the alkenyl, and we're looking at a bond order of about 2. And now we're in like the 1650 wave number region. So the energy has increased again. And then we'll go to the alkynyl, where we're at a bond order of 3. So the carbon-carbon triple bond having a normal vibrational frequency, where if it's hit with light around 2100 wave numbers, it will get excited and absorb that light. So we see patterns here. We see order. It's not random. So therefore, something must be happening. And we're going to talk about the properties and reasons for that today. So we're going to keep working down this group. And now we're going to the OH group. So we're looking at bond vibrations, single bond between oxygen and hydrogen. And as we know, that exists in alcohols, and when that OH group is connected to an aromatic group, that means it's a phenol. And this is a very diagnostic peak. It's broad and strong, and we're going to see that this one is very wide, very bold. It's probably one of the easiest ones to identify in an IR spectra. and it happens to absorb light in the like 3300 wave number region. Now, an OH group, a hydroxyl group, could be in an alcohol, but it could also be in a carboxylic acid. And again, remembering what that carboxylic acid is, that oxygen has a single bond to hydrogen. That's what absorbs now in like the 2500 to 3000 wave number region. But this hydroxyl group, that OH, is next to a carbonyl group. So it makes a carboxylic acid. But that particular oxygen-hydrogen bond vibration now doesn't fall in like the 3300 wave number, it falls below that. So around 2500 to 3000 wave numbers. Again, you don't have to memorize this, but we want to be able to use this table, and we have a whole bunch of examples we're going to go through, and we want to be able to come up with reasons for these patterns in a moment. The next type of bond that we're going to look at is the carbon-oxygen double bond, that carbonyl. So sometimes this could be in an aldehyde, where we have that carbon-oxygen double bond, and that carbonyl absorbs around 1700 wave numbers. This carbonyl group has a very strong diagnostic peak. It's very bold. It's one of the easier ones to identify. It's very intense. That carbonyl could also be in a ketone, and we can see that it absorbs in a very similar wave number region. A unique thing about aldehydes is that they also have that carbon-hydrogen bond vibration next to the carbonyl carbon. Ketones don't have that, so that's one little defining feature. And we could have a carbonyl in an ester. Again, it absorbs in a very similar region. We have that carbonyl group in a carboxylic acid, slightly shifted, but again, still in the same region, and an amide. So they all fall around that 1700 wave number region. We see a bold peak there. We know we have a carbonyl group. And then we have our amines, that nitrogen to hydrogen bond vibration. And they fall within the 3300 to 3500 wave number region. And sometimes they have a single peak, and sometimes they have a double peak. And we're going to see some examples of that as we move along. So we've seen some patterns here. Here we saw bond order changing the type of energy, as well as hybridization of the carbon changing the energy of the IR light that's absorbed. So now let's go into the theory of why this pattern exists. Once we understand it, then we can predict it and do useful stuff with it. So all of these bond vibrations that we're talking about and that we demonstrated last class, imagine that the bond connecting this atom to that atom is actually a spring. And it could be a really flimsy spring, or it could be a very stiff spring. But we're going to treat the bond as though it is a spring. And you probably learn about springs in physics class. And so we're going to use some of those formulas to talk about bond vibrations. So when we're talking about bond vibrations, bonds have a frequency, however many back and forth they do per second. Obviously, it's way faster than what I can demonstrate in class. The frequency of that bond vibration is proportional to the energy, right? Because we know with light, as frequency increases, energy increases. The frequency of the vibration is directly proportional to a force constant K. So it's a property of a spring. It's also a property of a bond. A stiffer spring vibrates at higher frequencies. We can see that they are directly proportional in this equation. The other term that we need to identify here is the reduced mass. Or I'm going to back up to K. Talking about the spring constant, because K is in the numerator on this side of the equation, if K is big, that's going to make the frequency of that vibration big, which means the energy is greater. So a big K means a greater frequency, which means a greater energy, higher energy vibrations. It will absorb higher energy IR light, light that has a higher wave number. Then we can talk about the mass of this atom and that atom. But we don't want to talk about two masses because it just gets mathematically annoying. So we have a reduced mass equation to take the mass of this atom and the mass of that atom and turn it into one number. And you have this formula here showing you how we can calculate the reduced mass when we take the mass of atom 1 and the mass of atom 2. The end result is bigger mass means bigger reduced mass. So reduced mass in this spring equation is now in the denominator. So if reduced mass is big, meaning we have really heavy atoms, big denominator means a smaller frequency, lower energy. So big atoms vibrate at lower energy. But if we had a small mu, a small reduced mass, atoms that are lighter, well, a smaller denominator makes the frequency bigger, which means higher energy. So lighter atoms vibrate at higher frequencies, higher energies, meaning they absorb that higher energy IR light at higher wave numbers. It all makes sense. It's beautiful. Okay, so let's continue on with that formula. There we go. The spring constant K is a way of talking about the bond strength. If we have a tighter spring from physics class, that means we're talking about a stronger bond in chemistry. Stronger bonds are tighter, requires more energy to break them apart, and they vibrate at higher energies. And we can remember that by seeing how it's directly proportional to the frequency, and frequency is proportional to energy. So let's look at some examples here. Here you have carbon-carbon single bond at a lower energy wave number. And we remember that energy is proportional to the wave number. Single bond absorbs in the 1200-ish region. Carbon-carbon double bond absorbs higher energy. Carbon-carbon triple bond absorbs higher energy. And we know that when we go from a single to a double, the double's stronger. Double to triple, the triple's stronger. As the bond strength increases, its bond energy, vibrational energy increases. So its bond frequency increases. It absorbs energy that's at a higher energy level. Stronger bonds, higher frequency for absorption. We can see additional patterns in this table here. Carbon-oxygen single bond to carbon-oxygen double bond. The stronger bonds absorb at higher energies. Carbon-nitrogen double to carbon-nitrogen triple. Again, the stronger bond absorbs light at higher energy. The pattern we need to know. Okay, what does that have to do with hybridizations? This explains the pattern of single to double to triple. When we saw the alkyl, alkenyl, alkynyl, and that pattern made sense. Tip, you can read some of these patterns from your table. So don't memorize them, figure out how to use the table and it can remind you of what those patterns are. We also had the pattern where an sp3 hybridized carbon versus sp2 versus sp hybridized carbon also vibrated at different frequencies. Think back to hybridization theory. To be able to make an sp hybridized orbital, what atomic orbitals did we put in? We put in an S, and we put in a P, and it gave us 2 sp orbitals. One way of thinking about that is that for an sp orbital, half of it came from S, which is spherical, half of it came from P. So an sp orbital is like half S character, round, close, half P character, dumbbell, and farther away from the atom. So we could say the sp orbital is maybe half of S character, meaning that it's spherical and it holds the electron density closer to the atom, which means it's a stronger bond. The carbon-hydrogen bond with an sp carbon, it's being held closer, held tighter. It's a stronger bond, therefore it vibrates at higher energy. Where did we get the sp2 orbital from? Well, we put it in s, a p, and a p, and we got sp2 hybridized orbitals. So you could argue, well, the character of an sp2 orbital is 1/3 s character, holding that electron density in a sphere closer to itself. And then sp3, we put it in s, a p, and a p. So we could call this 1/4 s character. Less s character closer to the atom, more s character, sorry, I said that backwards. Less s character farther from the atom, weaker bonds. More s character, atoms are closer together, stronger bond. That's my way of looking at this. And so that explains why we have higher energy vibrations with atoms that have more s character, lower energy vibrations with less s character. I'm going to skip this just for a second. We're talking about these properties because it's going to help us to be able to identify the peaks. We're going to talk about reduced mass when we come back, but then we're going to go through a whole variety of spectra and put this into practice and pull these pieces together and look at these patterns. But we're out of time for today. Have a fabulous weekend, and I will see you on Monday. Remember to bring your model kit next week. So I hope you look into that and find